Very good afternoon to all. We are going to start our second session of this FDP very soon. So I will request all of you to inform your colleagues or friends to join the session as early as possible. And speaker is also joining very soon with us. Thank you.
Hello? Hello?
Yes, sir, you are audible, sir.
Okay, okay. Acha, then I'll just check whether my presentation can be easily shown to you. Just a minute. Hello?
Yes, sir, yes, sir.
Ah.
Please share your screen.
Hello? Hello? Yeah. Just let me check whether sharing screen is. Okay. Then I'll just check. Just I'm checking it. Is it visible now?
Sir, 1 minute. We would like to start just now. Sir, 1 minute, please.
No, just I'm checking whether it is visible. My screen, is it visible now?
Yes, sir, it is visible.
Let me check whether it is now full screen. Is it full screen now?
Yes, sir.
Okay, okay, fine. So I'm now making it. Okay. Okay.
Hey, Chotto. Am I audible? Hello?
Yes, you are.
Yes. Very good afternoon to all. This is our second session of first day of our FDP, Advanced Material and their Characterization. Today we have very eminent professor, our guest, our speaker, Professor Dr. Shantanu Das sir, who is a professor and former head of Mechanical Engineering Department of Kollani Government Engineering College. He has previously served projects and development India Limited, New Delhi, and Dr. Babasaheb Ambedkar Technology University, Loner, Maharashtra. He did his bachelor's and master's in mechanical engineering from Jadavpur University, Kolkata in 1998 and 1990, and was awarded PhD from IIT Kharagpur in 1997. His areas of research include welding, weld cladding, machining, grinding, inventory management, application of multi-criteria decision-making methods, etc. He supervised 149 MTech theses and 104 BTech projects. He also guided so far 12 PhD theses and is guiding 5 PhD candidates also. He has published so far 191 journal papers, 37 book chapters, and presented or published 112 international conference papers and 176 national conference papers. He edited so far 15 books or proceedings. He is the chief editor of Indian Welding Journal, editor of Journal of the Association of Engineers, India, and managing editor of Indian Science Cruiser. He is involved in publishing Reason, a technical journal, a publication of Kolani Government Engineering College as the editor. He is also a member, International Editorial Board, Journal Sekta, published by Ahmed Dahlan University, Indonesia, as member, Editorial Board of Manufacturing Technology Today, etc. He is a reviewer of number of international journals and books. He is the secretary of Institute of Science, Education and Culture, past president and present chairman of Kolkata chapter of Indian Institution of Industrial Engineering. He is also the chairman of Welding Education Committee and Board of Examiners, ANB India, and chairman of Kolkata branch of the Indian Institute of Welding. He is now the vice chairman, School Research Committee of Maulana Abul Kalam Azad University of Technology, that is Macaut, West Bengal, Kolkata for Mechanical and Production Engineering Department. He has worked as a convener and also member UG and PG Board of Studies Mechanical, Automobile, Power and Production Engineering of this university. He has received some awards, and among them it may be highlighted that on September 5, 2018, he was awarded with Shiksha Ratna as an outstanding teacher from Education Department, Government of West Bengal, and Welding Educationist Award 2022 instituted by the Ultra Tech Times magazine, Pune, on November 26, 2022. He received Weldwell Specialty Award in 2021 and 2022 from the Indian Institute of Welding for the best MTech thesis in the area of welding being the guide. So today we are very eminent, we can understand. Today we are very much glad and very much privileged to have Professor Dr. Shantanu Das sir, myself Rajoshi Chakraborty, Assistant Professor from Department of Mechanical Engineering of Greater Kolkata College of Engineering Management. So I would like to hand over the session, our speaker, Professor Shantanu sir, to start his session. Shantanu sir, please, you can start, sir.
Thank you for the introduction. Okay,
Thank you,
let's just share the screen.
Yes, sir.
Is it visible now, my screen?
Yes, sir. Yes, sir.
Okay, let me now just make it full screen. Is it now full screen?
Not yet, sir.
In my case, it is full screen. Is there any lag or something, or?
Maybe, sir, here it is not showing, sir. Full screen not coming.
Oh, okay. Then I will just stop it again and try.
Yes, yes, yes.
Okay. Just wait. Is it now coming?
Coming same, sir. Not in full screen.
Not, I have not made it full screen.
Yes, yes. You can check, sir, now.
Yeah. Is it now full screen? I have made it full screen for my side.
No, not is coming, sir. You can start, sir. No issue.
Okay, let me try again. I just another time
Yeah.
I'm stopping it, and okay, let me check what happens. Oh, much. Okay. Is it now not full screen system has come?
Presentation is coming, sir.
Now let me try with the full screen. Let's
Yes,
check.
sir.
Is it now full screen?
No, sir. From your side it may be, but we can see in full screen, sir. Till now. Sir, you can start. No issue. It is also quite visible.
Is it now moving?
Not, sir.
Oh, in my side it is moving, but your side it is not moving. Then what happens?
That's why the lagging is happening, I think.
But this should not happen. Is it visible still now?
Yes, sir. First page is visible.
First page is visible. Let me check. I have made it full screen. Is it okay?
No, sir. Same, sir. First page, whatever it was before that one.
Is it visible? Can I continue?
Visible, yes. Yes, sir. You can continue, sir.
Okay. Now, like that, it is continuing now? Changing?
Yes, sir. It is changing, sir. Yes.
Okay. Fine. Then I can try with this, but some figures and tables may be a bit problematic because it will be then small one. No? I think now it is better. Is it so?
Yes, sir. Definitely, sir.
Okay. So, good afternoon, everybody. All the participants, dignitaries, whoever are present here, and I first thank the authorities of Greater Kolkata College of Engineering and Management, and particularly the Department of Mechanical Engineering, who have invited me to deliver this lecture in this 5-day workshop on advanced materials and their characterization. So today my talk is on exploring the possibility of using a CNT reinforced alumina-based nanocomposite as a cutting tool material. And this particular work we have started in collaboration with Central Glass and Ceramic Research Institute that is located at Jadavpur near your Jadavpur University. And a few years back, we have started this work when Dr. Premal Kumar Das was one principal scientist or senior scientist, something like that. It was his designation, and we progressed a lot. One complete master degree project was made to develop this CNT reinforced alumina-based nanocomposite cutting tools. Then a lot of tests were done at Kolani Government Engineering College facilities. And after that, Dr. Premal Kumar Das retired, and this particular work was stopped. It could not be continued. Recently, I found several other this kind of inserts lying with me. It was not found previously, and again we have started the work here. And let's hope that we will be continuing with this work with some more trials and tests and experiments, etc. And hope with CGCRI we can also continue this work, because new possibilities have come. Because that time, after the retirement of Dr. Premal Kumar Das, we could not continue due to some problems. But now I hope the problems are getting solved, and we will be continuing with the CGCRI with more new cutting tools development and tests to be done here. Now, before going to further on to this particular topic, I will just highlight what I represent. Actually, I represent here Kolani Government Engineering College, and this college was established in 1995. And at present, this college offers 5 BTech courses with mechanical, computer science, electronics, information technology, and electrical engineering. And mind that this college started in 1995 with 30 intake with 3 departments: one mechanical engineering, one computer science, and one electronics. And telecommunication engineering was the name given that time. Later on, this department name is slightly changed. And we can claim that we are the first department to start one MTech course in this college, and we started this MTech course in production engineering. And that time there was one collaboration with Central Tool and Training Center, one MSME institute under Government of India. But after first year, this particular course could not run, and we started our own syllabus and we started our own course. But the course name remains MTech in production engineering. Then next year, this computer science and engineering started their MTech course, that is in 2004. Then 2005, electronics and communication engineering, and later on, information technology and electrical engineering department also started their MTech courses. And along with this, there is Master of Computer Applications course, which is offered in this particular college, and it is unique in nature because no other government college offers this MCA course. And coming to Department of Mechanical Engineering, it offers BTech course since 1995, I have already mentioned, and 2003 we have started the MTech course. So pretty long time actually we are running. Now it is 2023. So 20 years old is the course of Master of Technology course offered by the Department of Mechanical Engineering. And we have good faculty and pretty good laboratory facilities, but obviously this lockdown caused some havoc with this particular problem because some of the facilities could not be run regularly and they are coming under repair, maintenance, etc. That is coming everywhere, and we are also suffering with this. And with the quality BTech final year project or even mini project, then master degree project works and also PhD works, we have done a lot of experimental, computational and other kinds of works, and ultimately good number of publications are made out of these works. That is one beauty of our department. And it is a center for conducting laboratory or practical classes of the Institution of Engineers India and the Indian Institute of Welding. We conducted 3 big size conferences, one in 2003, that was the biggest actually. After that, 2007, and just before lockdown, we have conducted one good national conference, 2019, and that was held with the centenary celebration of the Association of Engineers India. because they have completed 100 years in the year 2019. And apart from this, there are a large number of seminars, workshops, and expert lectures, webinars being conducted by the Department of Mechanical Engineering. So with this short discussion, what I represent, which college we represent, which department we represent, now we are coming to the actual topic. But before going to that, I can just mention, I headed the Department of Mechanical Engineering just about 20 years. Last year, the headship was relieved, and before that, I was heading this department for 17 years continuously, and before that, one gap was there, and again, somewhere around 2.5 years, I was the head. So, with this, I am just coming to the organization of presentation. So, first, I will introduce what is CNT, then what is the introduction of machining. Many of you may be knowing it. But I will again brushing up some of the things, because many of you may have been forgetting this one. Then introduction to cutting tool, then planning for CNT reinforcement in alumina, and then some works done at our college and at CCRI using the new cutting tool developed. That will be demonstrated here. So detail of the work, then typical results of machinability study carried out, and results and discussion and conclusion for each of the experimental setups and sets that will be highlighted. Then I will be drawing overall conclusion, then future scope of work, then references, some publications made out of this work, and the acknowledgement. So coming to introduction to CNT. Mind that CNT stands for carbon nanotube. CNT stands for carbon nanotube. So it is a typical form of your carbon, the element carbon. And you can see what is written here. Carbon nanotube is a new type of finite carbon structure consisting of needle-shaped tube, and each needle comprises of coaxial sheets of graphite, ranging in the number from 2 up to about 50. I will just show some of the figures. You can just see. I will show the next one. You can see the structure of this is something like this. So it is a cylindrical kind of structure, and that is actually having some sheet rolled into a cylinder. Then we have a lot of gaps between this. Okay, so these are typical kinds of structure of this particular CNT, that is carbon nanotube. Okay, and you can see carbon atom hexagons. Carbon atom hexagons are arranged in a helical fashion about the needle axis, and these needles are of 4 to 30 nanometers in diameter and up to 1 micrometer in length. So what our drawing is showing, that is actually giving some sketch of this particular typical structure of this carbon nanotube. So it is actually hollow cylindrical structure, but it is not a hollow cylinder. On the cylindrical surface, you are having some hexagonal sort of things. A lot of holes are there, and ultimately, this particular structure helps to achieve some typical properties. And these particular carbon nanotube structures are of two types. What are they? One is single-walled carbon nanotube. That means the carbon is having a single wall, very thin wall of that particular cylinder, that particular structure it is having. And it can be also multi-walled carbon nanotube, where more than one hollow cylindrical tubes can be put one after another in a coaxial fashion. And that becomes multi-walled carbon nanotube. And this is having the maximum application of this particular carbon nanotube or CNT in different areas. Okay, let me show that particular structure once again. And before that, let's see what is single-walled carbon nanotube, SWCNT. SWCNT, that is single-walled carbon nanotube. And it consists of one atom thick layer. Mind that it is just one carbon atom thick layer of graphite, and it is called, this particular structure is called graphene, and it is arranged seamlessly. There is no seam there. It is a continuous cylinder, and it is wrapped into a cylindrical tube. Okay, So a single wall of graphite, that is obviously carbon atom, is consisting of this particular, is there in this single walled carbon nanotube. These SWCNTs depend on the sheet direction about which the graphite sheet is rolled to form a nanotube cylinder. So graphite sheet with lot of hexagonal structure, lot of hollow items, and they are actually rolled to make that particular cylinder, and it is seamless cylinder. It is a continuous kind of cylinder. Okay. So that is a typical structure of this single walled carbon nanotube, and there can be different types of orientations. You can see these three diagrams. All these three diagrams are having slightly differences in orientations. The top one, that is the figure number A, it is having a straight kind of, if you just make the axis through these hexagons, then you will find it will be just coaxial or parallel to its axis, But whenever you see the second diagram, the figure number B, you will find this is of a different structure. Maybe some helical kind of structures can be found out if it is having the centers of these hexagons joined together. The C1, this is also having certain types of helical angle, but the angle is somewhat different. So structure-wise, this A, B, and C photographs are showing that there are some variations within its structure. This single-walled nanotube, carbon nanotube structures can be varied in this way. Okay. Now come to multi-walled carbon nanotube. Multi-walled. So it comprises of an array of such nanotubes that are concentrically nested like rings of a tree trunk. Okay. So you see, whenever a particular tree is growing, it is also making some concentric circles. If you just make a cross section, here also keeping the center of the axis same, you are putting here one tube after another tube, again another tube like this. In that way, you can increase the number of tubes to make one multi-walled carbon nanotube. And these multi-walled tubes generally have higher diameters than the single-walled nanotubes, and diameter here ranges from about 2.5 to 30 nanometers. And the interlayer distance in multi-walled nanotubes is close to the distance between graphene layers in graphite, approximately 3.4 angstrom. So this is a typical structure that can be made. Not everybody is capable enough to make these things, but you can see how will be the figure or diagram of this multi-walled carbon nanotube. You see here, three nanotubes are put concentrically one after another. The smallest diameter here is of blue color. Then green color one is the higher diameter with this compared to that of this blue color, and red colored tube is having the higher diameter than the other two layers. So in this way, here the typical structure of a three-layer multi-walled carbon nanotube is shown. If you don't have any, if you have any query in between, you can just stop me and ask also, or you can note it down and you can ask me at the later part. Okay. Now you can see what are the typical properties, or rather mechanical properties, this CNT is offering to all of us. There are some typical properties which are obtained due to this particular typical structure of this graphite. The simple graphite, you know, they are having some properties, but whenever graphite is converted to graphene with this kind of single-walled or multi-walled carbon nanotube structures, it gives some typical kind of properties. And what are they? See, carbon nanotubes are the strongest and stiffest materials yet discovered in terms of tensile strength and elastic modulus respectively. That is also one typical characteristics. Again, this strength results from the covalent sp2 bonds formed between the individual carbon atoms. And depending upon the synthesis method of CNT production and the variation on the measurement, the elastic modulus ranges from 270 to 950 gigapascal. Mind that if you consider one mild steel, its elastic modulus, that is Young's modulus of elasticity, is 210 GPa. But here, the CNT can have 270 to 950 gigapascal Young's modulus of elasticity, too high. And the tensile strength of the outermost layer can be ranging from 11 to 63 gigapascal. That is also very high. Okay, so these are the typical properties of the CNT. But mind that CNT alone may not be used in many of the cases, but you can put CNT into some other substrate material and you can improve the property, overall property of these mechanical structures or some other kind of structures. And mind that this CNT can be used to make the alumina somewhat toughened, and then you can use it as cutting tool material. That actually we have tried. Also, this CNT can be used as a one of the component or as one of the additives within some conventional cutting fluid, and then also it increases the effectiveness of this cutting fluid. Okay, in terms of cooling action, in terms of your lubrication action, etc. Even in some of the medical applications, these carbon nanotubes can be put there to put some stains, etc., etc. So there are various applications of this CNT, not only in structural applications to improve some typical properties, but also it can be used in some medical applications. It can be also used in some other applications, like it can be mixed with some cutting fluid so that cutting fluid effectiveness can be improved, etc., etc. And not only your carbon, but also some other nanomaterials may be added into cutting fluids to improve its effectiveness. That is also possible. Now let's go forward. What are the thermal properties of CNTs that it offers? Mind that we know that aluminium is highly conductive material as that of copper. But alumina, Al2O3, is highly insulating material, just opposite property. It does not offer any conductivity, but it gives you a lot of insulation properties. So we put CNTs inside alumina to improve some of its properties. Like this, CNTs have superior thermal and electrical conductivity, and mostly it is because of their nearly perfect atomic structure on the surface. So CNTs give you some thermal and electric conductivity. That is one important issue. Because alumina, we have insulating property. It is a very, very bad conductor of thermal as well as electrical systems. And some CNTs show high thermal conductivity in the order of 1700 to 3000 watt per meter degree Kelvin. And this is much higher than the thermal conductivity of copper of about 400 watt per meter Kelvin. So CNTs are giving you very high thermal conductivity. So a small amount of CNTs, if you can put into alumina in a proper fashion, then it can give some conductivity to this otherwise insulating alumina also. That is one important issue that CNTs can give. So with these typical properties that CNTs are offering, we are now going into introduce what are the typical fundamentals of machining. Maybe many of you are knowing it, but I am making it brusher because many of you may be forgetting also by this time. So after that, we will be showing how these CNTs are put inside alumina, and then some cutting tool materials are developed, and then how these machinability studies are made with that. We will show that. So when we introduce machining, you all know that what are the basic aim and objective of machining. So basic aim of machining is that to have 4 E's. One is effectiveness, one is efficiency, one is economy, and one is eco-friendliness. So previously we were not giving much importance on this eco-friendliness, but nowadays with a lot of pollution and all these things and a lot of regulations coming, so people are also thinking of making all the manufacturing systems, machining systems to be eco-friendly, okay, environment friendly. And what are the basic objectives? to enhance productivity or material renewal rate. That is very important because you have to produce certain objects by taking less time. Okay, that is very important. To improve quality, so you can make some items very fast, but you should maintain the basic quality what is desired. Then it should reduce manufacturing cost and to maintain overall economy and to minimize adverse impact on environment. So this environment friendliness or eco-friendliness is also one important issue nowadays that people are giving a lot of thrust. Now, what is the basic diagram of machining? Everybody knows, I am again telling. So you should have some raw material, and this raw material is a solid raw material in case of machining process. Then you are removing excess materials and ultimately you are making one product. And this product is becoming a product whenever it attains some typical desired size, shape, accuracy, then surface finish and integrity, and the desired mechanical properties. That means through the material removal process, you are adding some value onto your raw material to make it as a product. So this is very briefly what is known as a machining process. Now, if you consider one turning process, which is also one machining process, then you can see this is the diagram which shows the turning process, where turning is the diameter reduction process. And you are having some RPM, the rod is rotating. So from that RPM, you are getting one cutting velocity, that is VC is the notation here. And with this cutting velocity, with the feed given in a particular coaxial direction or parallel to axis direction, you are giving some depth of cut and ultimately material is removed and a lower diameter is produced out of the turning process. And if you try to define machining process, many of you are knowing machining, but we forget how to define it. So machining is a manufacturing process in which excess materials are removed gradually in the form of chips with the use of a wedge-shaped cutting tool. Mind that this is the basic definition for chip forming type conventional machining process. Number 9, there is also one category of machining which are actually non-traditional machining processes like your EDM process, ultrasonic machining, laser beam machining, etc. etc. But we are here talking machining to indicate chip forming type machining only. And you know what are the basic two angles. I am not going into very detail of these angles, but two angles are very, very important in case of machining. One is rake angle, that a cutting tool should be properly oriented, and one is clearance angle, that cutting tool flank surface should be clearing with the finished surface. So it is written here, the left diagram shows rake angle. So this one is the rake angle, and this one is the clearance angle here, and there should be a relative velocity between the cutting tool and the workpiece. So when the cutting tool and workpiece is having some relative velocity in the direction of VC here, this is VC here, then you are getting some material removed in the form of chips. So excess materials are removed in the form of chips. That is the basic uniqueness of this machining process, minded. And in the right hand direction, it is showing the side view of one turning process, where also the rake angle is shown and clearance angle is shown, and cutting velocity here in the tangential direction downward. And we normally define this rake angle as the angle of orientation of rake surface of the cutting tool with the reference plane. And this reference plane is a plane which is perpendicular to the cutting velocity. So in this case, this horizontal axis also is becoming the reference plane. But in the case of left diagram, you see reference plane is indicated as the vertical one, which is perpendicular to this cutting velocity. So rake angle becomes the rake surface and this reference plane in between angle. So this is very, very important because higher the positive rake angle, mind that forces will be reduced. That is the thumb rule. Okay. So suitable rake angles are used in different machining processes, and mind that in case of most of the ceramic cutting tools, we are using negative rake angles, where rake angle is negative, so force requirement will be slightly higher, but your cross sections of that particular cutting tool will be more, so heat conduction area will be more if it is obviously conductive in nature. And also you can use there double the number of edges of a particular cutting tool insert. That is very important. Now I am showing a realistic model, or not model, realistic photograph of a machining operation. Here, one left-hand cutting tool is used, which is moving from the left to right feed direction, and you are seeing some of the chip particles are coming out, and the shining surface, left-hand shining surfaces are the finished surfaces, and right-hand gloomy surface is nothing but the unfinished surface. So here also a turning, which is a machining process that is getting photographed. Now, you should know this very clearly that these are the cutting conditions. What are the cutting conditions? So VC, that is cutting velocity, is the most important cutting condition that gives the relative velocity between cutting tool and workpiece. Then feed, it gives the basic shape of the workpiece. If it is coaxial, then it gives cylindrical. If it is angular, it can give a taper. And then you require also depth of cut. So without giving depth of cut, your material will not be removed, because how much material will be removed, that is determined by the depth of cut. And environments can also be considered to be one cutting condition, because it is also very important, and many times it makes a lot of advantage to the machining. But sometimes it is disadvantageous also if the cutting fluid is not eco-friendly in nature. That is the thing. Now, machining can also be considered to be one MTFW or MFPW system. Why? Because whenever machining is done using some external power, it becomes a powered machine tool that you should use it. Like a lathe, where electrical power is there. Like a CNC milling machine, where also electric power is required for the main motions. So these powered systems should be there for higher productivity machining, and they are always you are using manual, machine tools. They are always you are using machine tools. But mind that machining can also be done manually. Whenever a carpenter is using a chisel and hammer and removing some material in the form of chips, then it is a manual operation. In a fitting shop also, using a chisel and a hammer, we are removing a lot of materials, and that also is a manual machining operation. Their machine tool is not used. But whenever it is a powered equipment for doing machining operation is getting used, then we call it as a machine tool, like a lathe, like a shipping machine, like a radial drilling machine, etc., etc. Then a machining always requires a cutting tool, obviously, because without a cutting tool, machining cannot be done. Obviously, chip forming time machining, I am telling. If it is a non-traditional machining system like say ultrasonic machining, or say electric discharge machining, or laser beam machining, there this kind of cutting tool is not required. There is a separate thing what is required there. Then fixture is nothing but some clamping devices. You have to clamp the workpiece, you have to clamp the cutting tool also. So appropriate clamping is very much required. Appropriate fixing of the cutting tool and workpiece is very much required for good and smooth machining operations to be performed. And obviously workpiece is required, because from the workpiece you are making the product. Now I am showing here the NH22 HMT lathe, which is available at Pune Government Engineering College, where a lot of machining experiments are being carried out. And here you can easily find out that there is a three-jaw chuck fitted here that can be seen here at the left-hand side, and one job is clamped within the three-jaw chuck, and there is a tool post on which you can put the tool holder, etc., in which the tool insert can be put, and machining can be done with the relative movement set and also feed and depth of cut set. Now, one important issue is machinability. So machinability actually is the ease of machining a workpiece material with a cutting tool material. Mind that one cutting tool material can be machining a particular workpiece material very easily, but it can fail miserably to cut different other, or to machine different other material. For example, say HSS cutting tool, it can machine my steel jobs very easily, no problem. But this HSS fails miserably if you want to machine on your stainless steel job. So that becomes a problem. Okay. So in that way, you should know that one cutting tool and one workpiece, this combination is very, very important to give you good machining capability. And there lies the importance of studying machinability, because one particular cutting tool can be very well suited for a particular workpiece, but it may not be suited for another workpiece. That should be always remembered, and hence machinability should always be judged as a combination of tool and work. So tool work combined must be considered to judge machinability. Now, how you can judge? That is also one very important issue. So we are telling what? It is easy. Easy means less effort is required. And whenever we are telling easiness, that means less effort, less energy, less power should be required. So that is the first thing. That magnitude of cutting force, power, energy, etc. should be low if you require good machinability. Then cutting temperature, because during machining a lot of deformation is taking place, and this deformation is also liberating some amount of heat energy. So this heat energy should be controlled as much as possible, so that cutting temperature rise should not be very high. That is also one important issue. Then the cutting tool wearing and tool life, this should be properly managed, because we require higher tool life, so that tools will not be reground or tools are not to be thrown away after reaching its life. So tool wearing rate should be controlled, should be as low as possible. Mind that we cannot stop tool wearing, but we can reduce tool wearing by selecting certain ways and means. And then surface quality. This surface quality of the workpiece should be as desired. It does not always mean that I should require very high degree of surface finish. It may not be, because surface finish sometimes we require very good, sometimes we require low, because surface roughness is the measure of surface finish normally. So lower value of surface roughness means high surface finish. But sometimes we require very high surface roughness. Where? Suppose it is a friction clutch. There is require a large amount of friction to be there, and that is given by rough surface. Okay. Even whenever we are cycling, we require some amount of roughness of the road. Otherwise, cycling will be a slipping. Suppose while we are cycling, if some sand, heaps of sand are there just below the cycle, what happens? The cyclists are getting falling down, because there the sand particles are making a third body system, and that reduces the friction between the road and cycle wheel, and ultimately it will be causing slipping, and ultimately the cycle will stop and it will fail. The cyclist will fail. Okay, so that is the problem. Sometimes we require surface finish, sometimes we require high surface roughness also. So, and another thing here is very important, that surface integrity. On the surface, there should not be any crack. Below the surface, there should not be any crack, as well as tensile residual stress. So from outside, it can be looking very good, but inside, if there is some crack is sitting or some tensile residual stress is there, then upon severe loading, maybe impact loading, maybe reversible loading, etc., this item can start cracking. This crack can propagate to the surface, and ultimately it can lead to some failure, fatal failure. So that also should not be there. And finally, whenever no other measurement system, etc., are available, you can just see what is the type of chip getting formed during machining, and that by also you can try to judge machinability. Mind that most favored machining chip is nothing but a long, continuous ribbon type chip. Long, flat, continuous ribbon type chip. That is the most favored chip form, obviously for a ductile material when it is getting machined. Okay. Now we are going forward. You should also know, whenever we are using some cutting tools, they are getting wearing out. At the end of excessive wearing, normally failure happens. But you can know there are three basic modes of cutting tool failure, and that is very important. Whenever you are judging the machinability, the cutting tool life, cutting tool wearing also you judge. So these three are the basic characteristics of the cutting tool failure. What are they? Mechanical breakage due to excessive forces and shocks. So that can happen sometimes to a particular cutting tool, specifically when the cutting tool is newly developed and your workpiece is very hard and brittle. That time, this kind of mechanical breakage of the cutting tool may happen, and due to some shock, due to some excessive force requirement, due to very high hardness of the workpiece, that may happen. Then quick dulling of the cutting edges by plastic deformation under excessive stresses and temperature. We are very much using high-speed steel cutting tools, and there is a limit. High-speed steel cutting tools, which are normally used, say T2 category, etc., they are having some restriction of cutting velocity, say 50, 60 meters per minute restriction. And mostly it is say 15, 20, 30 meters per minute people are using, because more is the cutting velocity, lower is the tool life, and you have to regrind this HSS cutting tool again and again. That also is becoming costlier. So why it is happening? Because HSS cutting tools are getting softened with the increase in temperature, and that softening tendency is very high. So whenever it is 15 to 20, 30 meters per minute cutting velocity, this heat involvement during machining is not that high. But whenever the cutting velocity increases to say 50 to 60 meters per minute, then heat involvement is becoming very high. So temperature rise becomes high. At that high temperature, HSS cutting tools or HSS materials loses its hot hardness property. Hot hardness property, what is it? At an elevated temperature also, hardness should be retained. And this property is getting lost corresponding to HSS cutting tools if you are going to higher cutting velocities. And mind that even if it is say 20 meters per minute and say you are getting tool life of several minutes, but if this HSS is used for say mild steel machining and you are rising the cutting velocity say about 60 meters per minute, then the life of the HSS tool becomes few seconds only. So you can imagine if the life is becoming few seconds, after few seconds again you have to take out the tool and again redesign it, again you come. So it is a loss of production actually. Okay. So in that case, what is happening? The HSS is getting too much softened at that high elevated temperature, which is made by the use of high cutting velocity. And that time, as the HSS material is getting lesser and lesser hardness, it becomes plastically deformed at its edge, because this edge can become some red hot, and ultimately it can be plastically deformed, leading to some sharp cutting edges are then lost. Okay, that is a very big problem for this kind of materials. And each of the materials you can have slight loss of hardness at high temperature, but in case of HSS or this kind of steels, loss of hardness at higher temperature is quite high. So third one is a regular one, that gradual wear of cutting tool at its flank and rake surface, and if it exceeds a particular value, then we call that it is a failure through gradual wearing phenomena. So all the cutting tools must be undergoing this kind of gradual wearing phenomena, and that should not be having any catastrophic breakage or plastic deformation. So this kind of cutting tools will be preferred always. The cutting tool only will be wearing slowly and gradually, and at the end of excessive wearing, it should fail. So that should be the phenomena of your cutting tool regarding its failure. Okay. Now, whenever we are going into this machining and all this cutting tool development, etc., you should also know very clearly what is the basic need of performing machinability study. Mind that machinability study is not new. Decades back, people were doing this study of machinability, and when it is required, particularly when in workpiece material is developed. Suppose the material scientist makes a hardest material, and he or she is very happy that okay, I have made a very extremely hard material, and that can have its typical applications. But mind that then the challenge comes to a machining person, how to shape it to a particular shape to make it a product. So that time appropriate machining strategy needs to be explored to shape it to a product to have its applicability. That is the very challenge. Because if you want to shape a particular very high hardness material, you should require a cutting tool harder than that. Because cutting tool hardness should be at least 1.5 times the workpiece hardness. So if you make on hardest material, then there is no other tool possible. So you have to find out some other material which will be harder than that. Then only you can machine it. Otherwise, you have to go in for these non-traditional machining processes like your laser machining process, plasma machining process, etc., etc. Okay. So for these different cutting tool materials, you have to try to find out the applicable ones. And with the cutting tool material and specific tool geometry found out, then you have to find out the suitable machining conditions at which machining can be done with good amount of machinability. Okay, that is the basic idea. So whenever new workpiece materials are found out, whenever new cutting tool materials are developed, then always you have to make some machinability study to find out typical geometry and material of the cutting tool and typical cutting conditions at which appropriate machining can be carried out. Okay, so that is the basic idea and basic requirement of machinability study. Now let's start how we have made this particular cutting tool, CNT based cutting tool material development. Okay, so okay, I will come to that point. Another two slides is there where cutting tool features are indicated. What is the need of new cutting tool? To provide high material removal rate and thereby achieving high productivity. That is one very important issue. Because HSS you are knowing by this time that it is a low speed cutting tool material, although the name is high speed, because more than 50 to 60 meters per minute you cannot go. Even 60 meters per minute is difficult. But you should note it that nowadays some HSS, special type of HSS are also developed, which can cut up to say 80-90 meters per minute also. Even some coated HSS tools are also found out, which can cut even up to 100-120 meters per minute also. That is possible. And to machine difficult to machine materials, you require some new cutting tool development. And to maintain economy by lowering cost and making easy availability of the cutting tools. That is also one important issue. So with these three things outlined, these are actually giving you what are the basic requirement of the new cutting tool development. But while going in for the development, you should know what are the basic properties that new cutting tool should have. And what are that? One is high compressive strength and high transverse rupture strength. So under some shock loading, under some usual type of loading, this should be having high amount of strength. It should not fail miserably. It should resist it. And mind that here, most of the ceramic cutting tool materials are very, very strong. And it is very strong in compressive strength, very strong in your transverse rupture strength also to some extent. But you have to put there some toughening agent, etc. Otherwise, it is problematic. Then it should be having high hardness. Hardness must be high because the workpiece hardness must be multiplied by 1.5 times at least to make the tool hardness. That is the basic requirement, mind that. Then enough fracture toughness. Because if you are not having enough toughness, then under shock loading or under tensile loading, the cutting tool material can fail miserably. So that should not be. Because alumina as such is a very, very hard material, refractory material, and it is having very poor toughness. So there are a lot of trials made by different kinds of researchers to make some toughness injected within this alumina. So we have done some work previously with CMERI Durgapur to make zirconia and yttria doped within the alumina to make it somewhat tough alumina-based material. Okay, that is there. Even some people have tried with silver, copper, etc., getting doped into alumina to make it tougher. And in this particular work, we have put inside this alumina carbon nanotube, multi-walled carbon nanotube to make it tougher and also to get some other properties height. Then high hot strength and hot hardness. I have already told hot hardness that if a material is having high hot hardness, that means even at an elevated temperature, its hardness can be retained to a large extent. And also hot strength means at an elevated temperature, the material should retain its strength. Okay, That is very important because during machining, you can have the rise in temperature in the order of say 200, 300, 400, 500 degrees Celsius usually. And if it is very high production, then it can be still higher. Then there should be chemical stability. There should not be any chemical reaction with the workpiece tool and the medium. Sometimes you are putting some cutting fluid that also should not react. It should be resisting adhesion and diffusion, because if it does not resist this much, then built-up edge formation, etc., can be very prominent, and that can give you bad surface finish. It can give you some vibration, immature tool failure, and all these things. So that also should be resisted as much as possible. Then thermal conductivity should be there, because whatever heat is generated, that should be conducted away as fast as possible. Then that is good. Otherwise, heat will be accumulated at the cutting tool edge and its surroundings. And there you require very high end property of the cutting tool material to resist that. Otherwise, if it is softened, then your cutting tool is getting lost. There is edge is getting lost there. So no more machining will be possible there. And then high density and elasticity is also another property, and it should be available easily and it should be of low cost. So that means economy should be maintained and availability should be ascertained. These are the basic requirement of any new cutting tool. Okay. Now I am showing how we have planned to make this CNT reinforcement within alumina. Now this basic development of this material was done at your CGCRI Jadavpur, Central Glass and Research. Central Glass and Ceramic Research Institute, Jadavpur. There actually this material is getting developed. They are having all these facilities. And I'm just showing how it is done. So you are knowing that alumina has excellent properties to consider as a cutting tool material. But one property it is lacking very badly. That is poor toughness it has. If toughness of it is high, then alumina alone can be a very good cutting tool material. But if as it is having very poor toughness, it can break into pieces if there is some shock load or some tension coming, etc. So we have to improve toughness by any means. And also another poor property is that is it is highly brittle, and also another is that poor thermal conductivity. So alumina is extremely hard, very good property, and refractoriness is there, but it is having poor toughness. It is having very low ductility, that means it is highly brittle, and it is having very poor thermal conductivity. So these things are to be improved. That is the basic idea, that people have tried to put multi-walled CNT, carbon nanotube, so that it can be reinforced within alumina to increase thermal conductivity, to have enough toughness, and also fracture toughness. So these are the basic idea that we can get by putting multi-walled carbon nanotube into alumina. That is a very important issue that we can achieve. And let's see how it is done. This multi-walled carbon nanotube reinforced alumina ceramic nanocomposite. So we call it as nanocomposite because carbon nanotube, these tubes are of nano size. So we call it as nanocomposite. So it is made of more than 95% pure multi-walled carbon nanotube, and it is having outer diameter of 60 to 100 nanometer and length is of 5 to 15 nanometer. And Messrs. Shenzhen Nanotech Port, China, from them the CGCRI has procured this particular carbon nanotube, because that company supplies quality carbon nanotubes, and it is also cheap compared to that of Germans, whose quality is good but cost is very high. So CGCRI has procured, in fact at our college also, and some people also have procured these carbon nanotubes from the same company to do some other works. And it is also procured that reactive polycrystalline alumina powder, which is 99.98% pure, and it is its diameter is of 0.5 micron in that range, and it is procured from Almatis Alumina Private Limited, India. So these two are the basic elements or materials what are procured from these two companies. Then For obtaining good dispersion of multi-walled carbon nanotubes in alumina, 1 hour ultrasonic agitation was employed using a bath solitaire, and it is made by Oscar Ultrasonic Private Limited India in isopropyl alcohol medium. So within isopropyl alcohol, we are putting their multi-walled carbon nanotubes for 1 hour under ultrasonic vibrations. So it is now getting sprayed, and there is no agglomeration, etc., that are taking place there. And the dispersed CNT suspension was then mixed with alumina and 0.5 weight% magnesium oxide powders using attrition milling for 3 hours in isopropyl alcohol using alumina of 3 millimeter balls. Okay, so in that way, alumina and multi-walled carbon nanotubes are mixed thoroughly. And the idea is that there should not be any agglomeration. At any point of time, it should not be only alumina. At other point, it should not be only multi-walled carbon nanotubes. It should be very well mixed. That is the basic idea. As homogeneous as possible, that is the trial. That is tried. And magnesium oxide was used to restrict abnormal grain growth of alumina during hot pressing. And it is followed by attrition milling, and then the slurry of 0.3 volume% multi-walled carbon nanotube, and that is there put into alumina, was dried up at 75 degrees Celsius in an air oven. And for normal this process is actually removing all these volatile materials from this particular mixture, because this isopropyl alcohol, etc., are volatile, that should be removed. So all these volatile materials are getting removed, and this particular item is dried up. And then hot pressing of the dried composite powder was performed at 1550 degrees Celsius at 2.5 megapascal uniaxial pressure with 1 hour dwell time under static argon atmosphere. And it is done to get sintered circular around 70 millimeter diameter disc of 5 millimeter thickness. So this particular alumina with this carbon nanotube doping within that, or it is not actually doping, it is mixed within that, and with that system we are making 70 millimeter diameter disc of 5 millimeter thickness. And during hot pressing, heating rate of 20 degrees Celsius per minute and cooling rate of 10 degrees Celsius per minute were used. And total 3 such discs were prepared for evaluation of the physical and mechanical properties, as well as to judge the machining performance of the hot pressed 0.3 volume% multi-walled carbon nanotube and alumina composite. So we call it as nano composite. So in that way, we have made 3 such discs of 70 millimeter diameter and 5 millimeter thick, and then from that disc we have cut small size your inserts to put into some tool holder to make the machining process. And this is the hot press unit available at CGCRI Jadavpur. There all this pressing is done. So here heating and pressing is done at the same time, and it is a very unique machine. Everywhere this machine is not available. They are having that, and ultimately they have made this particular ceramic composite, nano composite. And after cutting into typical shape, this shape is 12 by 12 by 4. So 12 is the edge length, 4 is the thickness. So that is the basic tool insert we have made at CGCRI itself. And if you see the microstructure of this particular nano composite, you will see these are the scanning electron microscopes of different magnifications of this particular material which is developed. So here the basic substrate is alumina, and on alumina you can find these small arrows are indicating, small green arrows are indicating small string type things. They are actually the multi-walled carbon nanotube. Okay, a small string, a small thread type kind of thing is there, small length. বাংলায় বললে কিচোর মতো একটু একটু দেখা যাচ্ছে, ফাঁকে ফাঁকে একটু একটু লেগে আছে, but this small amount of multi-walled carbon nanotube itself is giving this excellent property which are required to improve this alumina as a cutting tool material. Okay, and what are the properties they are giving? You see, I am showing this table. if you just compare with simple alumina, pure alumina, and this particular multi-walled carbon nanotube nanocomposite alumina material, bulk density you see gram per cc, this one is having 3.96, slightly improved than alumina. The relative density, it is also having slightly better, 99.58% than 98.67% in alumina. Vickers hardness, obviously it is Vickers micro hardness, it is 22.25, somewhat improved than the alumina. Flexural strength, so that is also very much improved. It is 372.8 and alumina is 341. But most important is this one. This is your fracture toughness. This fracture toughness is having a very good improvement, more than 1.2. It is the improvement in case of nanocomposite than that of alumina. Also, you can see another property here. Oh, that is not shown. So conductivity also is improved in this particular case. That figure is not shown here. Anyway, I have missed to include that slide. So conductivity is also improved of this nanocomposite than that of simple alumina. Now I am going to the machinability study that has been carried out at Colony Government Engineering College machine shop with different machine tools. And let's discuss. 3 different case studies I'll show. 2 case studies we have done quite a few years back. And till now we are again taking up this task, because we have found out some more this kind of inserts with us, and we have started applying it for different other materials, and we are successful to a large extent. So I am showing here the first case. So this is the machinability test, case 1. In this case, 11 kilowatt HMT length NS22 was used. And this particular experiment was conducted at IIT Kharagpur, because that time our college did not have this particular machine, but right now we have this machine and we are now using this machine itself. And the workpiece material was AISI 1060 steel rod, okay, and it is having 148 millimeter diameter and length was 450 millimeter. And the cutting tool insert was this one. What is the newly developed one? Tool holder is one right-handed tool with 25 millimeter shank, sandwich made. Cutting tool geometry is also this one. That is the negative tool, -6 degree, -6 degree, then 6 degree, 6 degree at the clearance angles. 15 degree is the auxiliary cutting edge, and 75 degree is the main cutting edge or principal cutting edge angle, and 1 millimeter is the nose radius. So these are the tool geometry, and the cutting conditions was varied from 149 meters per minute to 209 meters per minute. Feed was varied from 0.08 to 0.2 millimeters per revolution. So 0.08 you can consider as a finishing feed, and 0.2 is a roughing feed. Depth of cut considered was 1 millimeter and 1.5 millimeter. We have tried their dry condition as well as water soluble oil based wet condition. And dry wet test also was there with 102 meters per minute and 147 meters per minute at 2 feeds, and depth of cut 1 millimeter was kept constant. And we have used this AISA 1060, and it is having a typical composition, that is, it is having 0.63% carbon. So it is a high carbon steel cutting tool material, workpiece material. High carbon steel workpiece material, that is AISA 1060. And I can show it here some typical cutting force results with feed. Here the ordinate axis is cutting force and abscissa is feed. And here 3 direction forces are plotted. One is your Fx, that is the feed force. One is Fy, that is the axial force. Tool axis direction it is acting. And Fz is the tangential or main cutting force, what is there. So this firm line is corresponding to your Fz force, and you will find in all the cases there is a typical trend that with the increase in feed there is an increase in cutting force requirement. So that is the basic trend which is expected in all the machining experiments, and that is also replicated here. So the cutting tool material, that is CNT reinforced alumina cutting tool material, is also showing the similar tendency as that of a standard cutting tool available. So this particular condition is of dry condition and 1 millimeter depth of cut. So next one is corresponding to wet condition. Here wet condition means it is the lubricating oil, normal water soluble oil that is used here, not lubricating, it is water soluble oil that is used here. And here also we are seeing that all the force components are having a typical nature, that with feed it is almost proportionally increasing cutting force values. Px, Py and Pz, that is feed force. Px, Py is the axial force, y direction force, and Pz is the main cutting force, tangential direction force. All the forces are varying in a very similar fashion. Okay, and here you are seeing that there are 3 plots each. Each of the 3 plots are corresponding to 3 different velocities. One is for 149 meters per minute, one 179 meters per minute, and one 209 meters per minute. In all the cases, you have the similar kind of tendencies. Then, when 1.5 millimeter depth of cut is employed, you are also finding out that obviously the force value requirement becomes more, but the nature of force becomes same, that with the increase in feed, cutting forces are also improving proportionately. Almost with equal proportion, it is improving. Now, whenever the wet condition is used, the force values obviously are reduced, but the basic nature of the force variation remains almost the same. That means with the increase in feed, we are having almost proportional increase in the cutting force values. All the 3 values, Px values, Py values, as well as Pz values. And I'll show now the types of chips getting formed. Obviously, whatever chips I have told, that the most ideal or favorable chip is long, flat, continuous ribbon type. That kind of chip is not there, but these are very close to that. Here also we are getting that somewhat long continuous type. Sometimes it is hexagonal, rather not hexagonal, coil type. So if it is coil type, it requires somewhat more force or power than that of flat continuous ribbon type. So these top 3 conditions are somewhat close to this flat continuous ribbon type chip, but these are also continuous chips whenever it is a coil type, but it takes somewhat more force. So we always prefer to have long, flat, continuous type chip only if it is possible to have. And additional movement, additional surface features of the chips means you are requiring more deformation, and more deformation means requirement of more energy, more power, more force will be there, and that will be reducing your machinability. Okay. Then at the next condition, it is the 1.5 millimeter depth of cut. Here also you are finding that in many of the cases chips are getting broken. And if chips are getting broken with a lot of deformation coming up, then that also requires more force. So that is another thing that you can note it down. But here the third and second condition, top, middle and top right conditions, they are giving somewhat continuous kind of chips. And up to certain level, it is also long continuous ribbon, but it is not so long actually. So it is close to that part. So it is better. These 2 conditions are giving better chips than the others. Whenever wet condition is used with 1 millimeter depth of cut, we find that in most of the chips, actually it is all broken. And although wet condition means it should be lubricated and all these things, but here chips are becoming all broken. There is no continuous type chips getting formed here. And in this case also, it is wet condition with 1.5 millimeter depth. And in this case again, we find that 2 conditions, 179 and 209 meters per minute cutting velocity conditions, we are getting close to the continuous flat chips, but it is not exactly continuous flat, but it is somewhat irregular and continuous, and in between, in some portions you can consider it is a flat, but some other cases it is a bit irregular. But whenever the chips are getting broken through excessive deformation, then that takes more force usually. That is the thing. So wear tests are also done. I am showing here 2 typical wear tests. So at 102 meters per minute cutting velocity and feed of 0.1 millimeter per revolution, and with 1 millimeter depth of cut, we are seeing the progress of tool wear with machining time. And we easily find that with the increase in machine time, there is one increase in your tool wear values. So the square symbols are corresponding to nose wear, and the triangular symbol is corresponding to the average flank wear. And in this case, you can find that even after 14 minutes of machining, we are getting average flank wear value, say around 160, etc. micron. And we know that up to 300 micron ISO allows normally to continue with a particular cutting tool during machining operation. But here we are finding that up to 14 minutes, we have got only 160 micron. So 300 micron is far, so we can continue further with this particular cutting tool insert. And in that way, nose wear is somewhat more, but okay, flank wear, average flank wear, that is VB we call, that is the most important your cutting tool wear feature, and that should be restricted up to 300 micron maximum. Another test also we have done, that is corresponding to your cutting velocity 147 meters per minute, feed of 0.05 and 1 millimeter depth of cut. And here also we find the very small value of tool wearing is observed here, and up to almost 6.5 minute. Less than 50 micron average flank wear is possible, but the nose wear becomes too high. It becomes slightly less than 200 micron at the end of 6.5 minutes of cutting. At the end of this machining, if we see the types of tool wear, you will find a typical case I am showing that here there is a band of wearing taking place, and it is very clearly understood. From the top, the shining part, the bottom of the shining part, this distance is basically the principal flank wear part, which is shown as a shining part. And nose wear part is also shown at the right hand side. Okay. So average flank wear is shown, and this value is somewhat low, obviously. And if this value is becoming 300 micron or more, then it should always replace this one with a new one or grind it. But these are all ceramic cutting tools. These are in general non-grindable. These are all throw-away type of inserts. Okay. Now, what conclusion we can draw out of this case one? So this particular thing is already published in one conference series paper and also in Journal of Association of Engineers India paper. So increase in cutting force components with increase in feed expectedly due to increase in chip load and manual and metal revert that occurs. Okay. Increase in cutting force components with increase in feed expectedly is done, or expectedly it is observed due to increase in chip load and material removal rate. The chip load is getting increased with the increase in feed. Then variation in cutting velocity did not yield much variation in cutting forces, that is found out. Then long flat continuous chip is formed in some machining conditions, rather near to this I should say, which can be considered to be favorable. And finally, it can be stated that the newly developed 0.3 volume percent multi-walled carbon tube or alumina insert is having good capability to turn AISI C1060 steel rods in wet condition and can be applied in machining industry. Actually, this C should be omitted. It is AISI 1060 steel. So this we can conclude that this particular range of cutting velocities can be adopted so that materiality can be found good in this particular condition. Now coming to the case study 2. Here we have done this study at our lab only. Here turnmaster kiloscale lathe was used, and here AISI 4340 steel rod of 38 HRC has been used. And same tool holder, etc. is used, so tool angle will be similar. There is no change. Here cutting conditions, two cutting velocities are taken, 118 and 172, and feeds are varied 4 times, 0.05 to 0.11 millimeter per revolution. Depth of cut is chosen as 1.5 millimeter, environmental condition dry, and nose radius is varied from 0.8 to 1 millimeter. 0.8 to 1 millimeter. Now, these are the basic workpiece composition of AI SI 4340. So, carbon is not much, lower side carbon is there. Manganese is 1.29%. Then chromium is 1.1%. That is important, and vanadium and niobium is also there to some small percentage. So these are responsible for its somewhat higher hardness. Okay. Now, what are the experimental conditions? Experimental conditions are something like this: 118, 172, 118, 172. So total 60 experimental runs are conducted in these two sets, and feeds are varied 4 times: 0.05, 0.07, 0.09, and 0.11. And nose radius is varied 2 times. So total 16 experiments are conducted using these variables. Okay. Now, if you see the variation of cutting forces here also, it is very clearly visible that at both the cutting velocities 118 and 172, we are having almost a particular clear trend that increase in main cutting force, increase in main cutting force and feed force, rather the horizontal force is in a continuously increasing manner, or this trend is very clearly visible here from this particular plot, as similar to that of any standard machining cutting tool. And chip, here you can see that most of the chips are either irregular or conical, helical, etc. chips. So sometimes it can be stated that okay, whenever chips are of more flat and continuous in nature, that can be considered. So in that way, also you can identify some of the chips which can be considered to be the good quality chips. Okay, and which will be desired, etc. So from this particular set of experiment, it can be concluded that at cutting velocity of 118 and 172 meters per minute, machining can be done satisfactorily with formation of long, continuous, irregular or open coiled chips without any built-up edge formation. Cutting force readings with the inserts having 0.8 and 1 millimeter nose radii showed consistent variation with the change of feet. And the second one, the newly developed 0.3 volume percent multi-walled carbon nanotube and alumina tool insert shows its prominent efficacy to turn AISA 4440 steel rod in dry condition, and therefore can have the possibility to apply in machining industry. Now another and the last case study I will just tell you. I think I am just crossing time. Maybe I am getting 5 minutes more. Hello?
Yes,
Can
sir.
Okay. So if I conclude here with this, just a minute. Okay. I have told already this one. So this multi-wall carbon nanotube and alumina cutting tool insert is showing its prominent efficacy to turn AISA 4340 steel also. So that is one thing we have made, and here these two cutting velocities were identified to give good amount of machining ability. Now I am coming to the third case study 3. So this is an interesting result. I will not show this result much because we have not yet published. The work is going on. Here, multi-walled carbon nanotube based nanocomposite, alumina nanocomposite is used as the cutting tool, and the workpiece material here again is a new one. This workpiece material is newly developed by CME, CSIR CME Durapur, and it is a aluminium base Mg2Si and Si metal matrix composite. Okay, within aluminium base you are putting there magnesium silicate and then only silicon. These are put at some proportions, and this is also having good HRC. 38 HRC is there. Hardness is somewhat good, high, and as it's the new material, the machinability study on this new material with this new cutting tool we have tried. We have also tried with different other cutting tools. So today I am not showing all those results, but this CNT nanocomposite cutting tool is used to try to machine this aluminium based newly developed metal matrix composite. And here we have used a design of experiment method which is known as response surface methodology, RSM it is popularly known as. And within RSM, central composite design, that is CCD design of experiment we have resorted to, which is done with 2-factor 5-level experimental system. Here cutting velocity varies from 68 to 185 meters per minute. Feed is varying from 0.06 to 0.16 millimeter per revolution. Depth of cut is kept constant as 1.5 millimeter and environment is kept dry. Okay. Now I'll just show some samples of results what are available here. Now let's just put what are the typical specialty of this particular workpiece material. AL-MB2-SiSi aluminium based metal matrix, or known as AMC, aluminium metal matrix composite. This newly developed AMC may find its huge application due to its low density, processing flexibility, heat treatment capability, and high wear resistance and improved elastic modulus and strength. So you know that most of the aircrafts are made of aluminum based materials. So this material can also be finding out its application in this kind of low density requirement applications. Then MD2Si is a hard intermetallic compound and it has high melting point of 1085 degrees Celsius compared to that of aluminium. And this particle size can be changed abruptly with increase in cooling, and heat treatment with appropriate parameters can be an effective way to improve the microstructure and properties of this material. And now I am just showing one typical result of it. Here it is the feed value and here is the cutting velocity value. How feed and cutting velocity is influencing the main cutting force that is plotted here. So this plot is corresponding to the main cutting force or PZ component, tangential cutting force component. And you can see the color table here. The light green color is corresponding to less than 80 Newton force, but very dark green color is corresponding to more than 140 Newton force. So you can easily find out that this particular region, this is the very light green region, is corresponding to the lowest main cutting force requirement region. And it is natural that at a low feed and at a moderate cutting velocity, you are getting this particular region where less force, energy, and power will be required. But as it is lowest feed, your productivity is somewhat less. But for finish timing, you can use this particular condition. Okay. And if you see the chips, you'll find in most of the cases these chips are all fractured chips. And it is quite natural because this particular aluminium base composite material, here aluminium is ductile, but whatever materials are added within this, these are all hard materials. So with the influence of this hard material, this aluminium base matrix composite is also becoming somewhat hard, and ultimately hard materials are getting fractured easily. So all the chip particles are getting small length fractured chips generated. Okay. And another thing is that here, whenever you are using multi-walled carbon nanotube base alumina cutting tool material, mostly there is no built-up edge formation. Otherwise, in other conditions, if you are using some carbide cutting tools, lot of built-up edge formation is getting made. So here, built-up edge is almost absent, and that is one advantage because there is no bonding between this carbon nanotube based alumina and this aluminium as such, aluminium based composite material. Okay. And you can just put a short conclusion that at a range of cutting velocity within 110 to 140 meters per minute with a feed of 0.06 millimeter per revolution, machining can be done satisfactorily, requiring less main cutting force. This is one thing. And cutting forces show an increasing trend with the increase in feed naturally. And the newly developed 0.3 volume percent multi-walled carbon nanotube and alumina cutting tool insert showed its prominent efficacy to turn this AlMg2 SiSi aluminum base metal matrix composite rod in dry condition, mostly without built-up edge formation, and therefore can have the possibility to apply in machining industry. And if I just put in an overall conclusion, I can just tell here that multi-walled carbon nanotube reinforced alumina nanocomposite cutting tool insert developed is found to have superior fracture toughness, hardness, and other mechanical properties that indicate possible suitability of it as cutting tool material. At the chosen machining conditions, the newly developed insert shows good machining performance, providing consistent variation of cutting forces while turning two kinds of steels and an aluminum-based metal matrix composite. The developed cutting tool could be successfully used over a wide cutting velocity range and moderate feed and depth of cut. Now I show some of the future scopes where people can try further works. Different additives may be tried with appropriate proportions to achieve higher wear resistance. Then cutting tool geometry parameters may be optimally set to improve machinability of the insert developed while machining different grades of steels, etc. These two are the basic scopes what I find. And under the references, I am showing some of the good references. First paper was a paper of Professor A. Chattopadhyay and others. So there are very good works done by Professor A. Chattopadhyay in collaboration with the Department of Metallurgy and Material Science of IIT Kharagpur there. And also worldwide, many other persons have started doing a lot of works. Even carbon nanotube also was tried in some other works. And CSRI has used and tested carbon nanotubes for different other applications, maybe rocket applications, maybe other high temperature applications. And this is not new as such for them, but use of carbon nanotube based alumina as a cutting tool material is a new one that we have progressed to a large extent. And then some publications were made and still some are in progress. I am not showing them. These are somewhat old publications. 2014, the Snehashi Sarkar was the person who did MTech project at Kollam Government Engineering College, and he actually did all these initial developmental works. So 2014, 2016, and 2018, these four are the basic publications there. Few publications are still in process. And one thing I can just mention, the last publication shown here, it is in the Journal of the Institution of Engineers India, Series C. It is a Springer publication. And this publication was awarded as the Production Division Award 2019 by the Institution of Engineers India. Okay. That we have got, rather our team got that. And finally, I acknowledge CSIR and CSIR CCRI, Jadavpur, CSIR CMERA Durgapur, and also Mechanical Engineering Department of IIT Kharagpur for giving a lot of opportunities there to do this development and experimentations. And obviously, most of the works are done at Kollam Government Engineering College at their machine shop itself. The MTech PE students, namely Snehashi Sarkar and Suman Kumar De and a PhD scholar Dipannita Vishwas, who did or are working with CNT reinforced nanocomposite and on the machinability study involving it are thankfully mentioned. Snehashi Sarkar completed MTech quite a few years back, and at present, Suman Kumar De is applying this insert in his MTech project, and Dipannita Vishwas is employing this one in her PhD project work. Thank you for your patient hearing. Any question?
Audience, we would like to ask that if you have any query or any questions, sir is there. Please ask. You can ask, please. Feel free to ask, and it's a nice presentation. We are really glad to have sir, and sir is giving us time, and really nice presentation that we are having after a long time, sir.
Okay.
Anybody has yes, sir. Anybody has any query or question, please ask. And one thing, we have given already the feedback link in our chat box. All are requested to fill up this one also. An assignment link also has been given. Please check. Anybody has any question?
No question. Okay.
I think no queries are till now.
So there can be two possibilities. One thing, everybody has understood everything, which is quite
Yes,
unlikely,
sir.
or nobody has understood anything. I don't know. That is correct. Uh, but I tried to tell as simply as possible.
Yes, sir. Yes, sir. It is. We are. I mean, we are hearing as a mechanical student from the very beginning, not from MTech, not from BTech. We are hearing, and we are really much fan of Santanu sir. We all know, and we have Tanvir sir as well as Somik sir also in our department.
Yes.
They are also the student of yours, sir.
Yes. Yes.
So anyway, we are going to end our today's session, and we are very much pleased and thankful to sir that sir has given us time and sir has well presented everything he can do, and really thankful to the MTech students as well as the PhD scholar also Snehasis and Dipanita madam, all that they have presented or they have made the presentation, all that with sir. Really great, and we are really pleased, and will be really thankful if we can do some work with sir also from mechanical department, sir, if it is possible in future.
Yes, yes, it is possible. You can make on MOU also with our college because from JS group, I think we have already entered on MOU with Sudhi Chandra Sur.
Yes, sir.
Yes, Kollani has visited, that Sandeep has visited. He's also our student.
Okay.
And they are also talking to make on MOU. Even without MOU also you can do some work, no problem. It's welcome. Only thing is that people should give time and do some work.
Yes, sir. Yes, the main thing is that
Yes.
we can give time, sir, but thing is that you are really very much busy, sir. We know, sir. We have to go and we have to discuss. We will discuss with our department also that how can we can collaborate and how can we can work, as well as civil team also, civil department also with us. Our civil department HOD sir, Mr. Subhajit Chotra sir also with us. Civil department also with us. Yes, Sucharita madam is telling thank you, sir, in chat box. All really all are very much pleased and all are very much thankful to you, sir.
Okay.
Okay, we are concluding here, and before concluding, we are once again we would like to thank Antunu sir once again, and really thankful our principal madam. Without her cooperation, without her insist, we can't proceed or we can't complete this FDP. We can start. We are thinking from very beginning, but without her initiative, we can't complete or we can't start this FDP. As well as our HOD, we would like to thank our HOD sir, Dr. Tanvir Islam sir, and civil department HOD and team, our Chotrat sir, Subhajit Chotrat sir, and all the participants. We really thankful to them also. They are listening and they are participating with us. Thank you. And we are concluding here. And this is a small token of appreciation, sir, from our end, from our Greater Kolkata College of Engineering, from Mechanical and Civil Engineering Department that we are organizing. And you are here, you are presenting. So this is small token of appreciation, digital memento we will be mailing to you, sir, very shortly.
Okay.
Please accept, sir.
Thank you. Okay.
Yes, sir.
Okay.
Thank you. And it is also being live streamed in our YouTube channel from college. And from there also very much all India participants are attending this program, sir. Thank you all.
Okay, okay. So what is that link actually? Like
YouTube link.
YouTube link?
Yes, sir.
Yeah,
Yes, sir. It is also in our group. I will request Tanvir sir to share in the chat box.
Okay.
Tanvir sir, are you there?
Okay. I will send it. I will send it to sir.
Sir, Tanvir sir will send you, sir.
Okay, and one thing I should point out, I have made some question answer. No, I think one answer is to
assignment.
One answer may be a bit modified. I'll send that answer key afresh. Questions are all right.
Okay.
One answer I think needs some modification. What I find. Okay, I'll send it to Tanvir. Okay.
Okay, sir. Okay.
Okay,
Thank you,
sir.
sir. We are concluding. Thank you, sir. Thank you so much, sir.
Bye.
Thank you all. And we will request all the participants to join again from tomorrow onwards. Around 11 a.m. Around 11 a.m. onwards from next session from tomorrow. Once again, thank you all. We are concluding here. We are ending. Thank you, sir. I will request host to conclude and end the session, please. Okay, all of you, please join from tomorrow 10 a.m. onwards, as per schedule, please. And the host requesting you to conclude and end the session, please.
मतलब है वो चीज, बट प्रॉब्लम क्या है ना सर,